At Infineon, our deep understanding of solar, wind, and power conversion allow us to optimize products to deliver the high efficiency, performance, and reliability needed in these applications, such as our cool SiC solutions for best-in-class efficiency and our Easy Power Module family for flexibility and scalability. Solar installations use different types of inverters based on their power range. Microinverters are designed for up to 1500 watts and require a compact and high-efficiency design. Our Optimos MOSFET and Cool SiC diode families are ideal for the DC to DC stages, while our Cool MOS offering is recommended for the DC to AC conversion. Multi-level string inverters up to 5 kilowatts can take advantage of our low-voltage Optimos MOSFETs and the reduced conduction and switching losses. String inverters up to 10 kilowatts will benefit from Cool SiC MOSFETs and diodes or IGBTs in our high-speed 3 and trench stop 5 families, while inverters exceeding 30 kilowatts are best served by the high density and high efficiency provided by our module solutions, including Easy Cool SiC, Easy Booster, and 3-level Easy 1B, 2B, and 3B products. In central inverter solutions, 2-level or 3-level NPC1, NPC2, or ANPC topologies are preferred. A 3-level topology is widely used as it enables higher efficiency levels. Our Econo Dual 3 family, 62mm modules, and PrimePack 3 and 3 Plus modules are best fit to create inverter solutions up to 3000 kilowatts. Wind turbines, which are typically rated from 1 to 10 megawatts, require power electronics to deliver high power density while providing robust and reliable operation for up to 25 years. Infineon's PrimePack 3 Plus modules, leveraging our IGBT5 and DOT-XT joining technology, offer up to 25% higher power density or a 10 times longer lifetime in wind power applications. The overall performance of renewable energy generation benefits from energy storage systems that balance fluctuations in demand and supply. Whether these are utility, commercial, or residential storage solutions, they require power conversion and battery management systems. If you design power conversion systems up to 30 kilowatts, the best choices are discrete Cool MOS, Cool SiC, and Optimos switches, while Easy and PrimePack power modules offer efficient design for energy storage systems with a higher power. Infineon's comprehensive portfolio meets the requirements for your system solution based on our Cool SiC, highly reliable IGBTs, and power MOSFETs in both discretes and modules. As every switch needs a driver, our offering includes optimized gate driver ICs complemented by sensing, control, and security components. Learn more at infineon.com/solar.
Thank you very much for the kind introduction. And my name is Emmanuel Gia, as just mentioned. I apologize for maybe I will have a sleepy face. It's about 2 a.m. here in Canada, and I just arrived from Icon about 7 hours ago, so permit my lack of coffee face. And like he just mentioned, just a brief introduction about myself. I did my bachelor's in Nigeria, my master's in South Africa, and now I'm doing my PhD in Norway, and I'm a guest researcher in Canada. So I probably can say that I was made in Africa, and I'm being perfected in Europe and North America by an Asian supervisor. So I'm quite complete around the globe. So I'm at the University of Agder in Norway. So this is the map of Norway, and we're at the southern, I guess the southernmost part of Norway. This is Grimstad, where our engineering faculty is located, and Kristiansand, where the main university campus, the bigger university campus, is located. Probably the Kristiansand campus is actually the southernmost point, not Grimstad, yes. So I will just be giving an introduction about power converters generally and introducing multi-port converter topologies, and be discussing some of the topologies that we have proposed, our validation method, and then I will present some challenges and opportunities for future improvement. So The recent developments of the energy markets in Europe and across the globe generally has, especially in Europe because of the war, has increased the need for a more decentralized energy market, a more decentralized generation of energy, especially when it comes to and renewables generally are strategically positioned to achieve this decentralization using wind and solar. And as we can see here, the projected the projected growth in energy supplied by the International Energy Agency (IEA) is projected. It is projected that solar and wind will continue to increase up until the projection up until 2026 in all both the main case and accelerated case projects that solar and wind will continue to increase, even though in the past decade there has been already more than 33% increase in the global demand for electricity. So there continues to be need for more investments into more efficient energy utilization, and now more than ever before, decentralized generation is now much more important. And power electronics systems such as DC to DC converters, DC to AC, AC to DC, different forms of conversion are at the center of this drive and demand for more efficient and flexible utilization of energy, specifically with the penetration of renewables and energy storage systems. We know the reason why we have to combine several different types of renewables, such as wind and solar, because these are intermittent sources of energy that, like, for example, when the sun is down, the PV production is completely down, and when there is no wind, the wind generation is completely down as well. So there is need for integration of these systems for different applications like grid systems or electric vehicle or some other microgrid systems or applications, and even for storage systems, because these storages have different uh, power or energy densities. There is a need for effective combination of these systems like batteries, which have very high energy density, and supercapacitors, which have very high power density, to combine these two uh, different technologies to have a balance of both high power and high energy density in the energy mix. And so the use of single input converters has been the traditional case over the years to integrate these systems to a DC grid or even to an AC grid. And the use of single input converters comes with a lot of challenges because you need a lot of components, a lot of different systems, and then sometimes you need to it is more difficult to coordinate the controller. And so research has been going in the direction of investigating the possibility of using a multiport converter, for example, for energy storages, to combine battery and supercapacitor, just like the first presenter, Mr. Bang, discussed. And so even without the need for this, to reduce, as part of the drive for reducing the number of components, especially semiconductors, that are being used in these systems, the 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 shortages in the semiconductor industry is actually another key point to look at, to providing more and more efficient ways of utilizing semiconductor devices, especially in power converters, because there is a lot of demand for semiconductor devices, both for other applications such as in vehicles or some other components like computers, laptops, mobile phones. So there is this huge competition and uncertainty in the whole semiconductor market. So it is now more also very important that multi-port converters can be considered for application in microgrid or other kind of microgrid applications, such as in aircraft systems or electric vehicles for combining energy storages, or stationary applications like in household grid systems. So now to go into the multiport converters, there are different types of or different categories of multiport converters. We have the isolated and the non-isolated. The isolated are are named as characteristically as isolated because of the use of isolation transformer or coupled inductor in the isolation of the primary and the secondary in, or the inputs from the output of the converter, as in this case, the multiple inputs are introduced using pulsating voltage sources, and then a dual active bridge converter as a secondary converter is used to isolate the input from the output. And in the non-isolated case, there is no isolation between, there's no magnetic isolation between the input and the output. And so in another category is the multi-outputs based on the number of outputs of the converter. So for example, in this case, this is another multi-active bridge converter using a four-quadrant transformer. So it's able to have two inputs and two outputs as well. And also this is another multi-output multiport converter, which is non-isolated. Another category of converters, of multiport converters, which I have not presented here, is based on the possibility of arbitrarily extending the number of input ports. So for example, in this case, the number of input ports can be increased by introducing two switches or one half bridge and the input source. And in this case, another input can also be introduced by introducing a half bridge, an inductor, and the input source. And also the same for this case, it can be another input can be introduced by just introducing a single unidirectional switch. And in this case, you will have to do more modifications because you have to increase the number of cores, because for every additional input you need one more primary side to this transformer or coupled inductor, whichever is used in the application. So there is those converters that you can arbitrarily increase the number of inputs, and there are converters that have, based on their structure, have a very fixed number of inputs and number of outputs. So that's another class of multiport DC to DC converters. And so going into how these converters are synthesized, first, there are broadly two main ways of synthesizing multiport converters. One is by synthesizing, I mean how they are designed or how they are made. One is from the basic single input converters. This is a standard 4-switch buck boost converter, as we all know. And if we look at this converter that was proposed by in 2015 by Andrew Hinz and his colleagues, you will see that the topology is very similar in terms of the structure. And so this is basically how multiport converters can be synthesized from a single input converter. Basically, additional ports are introduced by just introducing the half bridge at the input and the filter inductor. And this is what was done here. And so to further modify this topology, we also introduced a converter based on the 4-switch converter, the basic 4-switch converter, in which we tried to keep the number of inductors used fixed, so that we use less components as compared to this, and we're able to introduce additional inputs with just introducing the bidirectional switch. So this is an example of synthesizing converters from the basic DC to DC converters. Another interesting method which has been proposed by my colleagues here at University of Alberta, is the synthesizing of DC to DC converters, multi-port DC to DC converters based on graph, should I say, graph theory or graph-based generalization. And this is basically synthesizing another DC to DC converter from an existing multi-port DC to DC converter. So this is a multi-port DC to DC converter. They created the graph-based generalization of the converter and then modified and created another kind of multi-port DC to DC converter based on the existing topology. So with this method, they're able to create more topologies just by rearranging the components. But in my opinion, although this gives you a different kind of converter, might be useful for a different kind of application, but it doesn't really like reduce the number of components or change the number of components in so many ways. It can change the position of some components for some advantages, but it cannot really yield a reduced or smaller number of components utilization. And I will mention why this is very important in the next slide. Yes, so the key areas for improvement in multi-port converters is that we want to reduce component counts so that we can reduce cost. We want to reduce complexity of control as much as possible, and also explore the possibility of high voltage gain. So in this slide, like I mentioned before, we proposed this multi-port DC to DC converter based on 4-quadrant switches. Basically, that's a fancy name for bidirectional switches as described here. So the current possibilities for implementing bidirectional switches, either using common emitter or common collector configuration, or using 2 reverse blocking switches as displayed here, placing them in anti-parallel such that when one switch is triggered or one switch gate is turned on, the current can flow from one direction, and then the flow of current is blocked in the other direction. While when the other switch is triggered, the flow of current can go in the opposite direction. So, or as in this case as well. So in this converter topology, we're able to achieve a multiple number of ports, and we're able to arbitrarily increase the number of ports, which is a huge advantage in terms of the robustness of the converter, by just introducing one extra switch and the input source. So one key area of improvement is that we were able to keep the inductor fixed, as I mentioned. So the key advantages of this topology is that we have reduced number of switches, we have a fixed number of passive components, and we introduced a simple control based simple duty cycle control, which we have published in the Transactions of Industrial Electronics. I've put the reference here for further reading. I decided not to talk too much about the steady state analysis because there are other topologies that I want to discuss, and the result as well. So I would indulge you to go through our paper in both the conference paper that we presented at ECC Asia last year and the CIE that was published, I think, earlier this year as well. So this we were able to, based on a reduction of number of components, we were able to uniquely improve the qualities and the control robustness of this converter as we discussed in the paper. Another converter that we proposed was a flyback based converter. So we used the standard flyback converter, but we tried to introduce more number of inputs by using a reverse blocking switch and introducing the input port directly. And one key feature of this is that we can only use this for renewable energy sources, because this is not a bidirectional switch and this is not a bidirectional converter. So we cannot integrate like battery and supercapacitors using this topology. And another limitation of this is that because of the traditional limitation of flyback converters, we cannot use it for very high power converters. So we did not really explore this topology beyond presenting it in a conference. And although based on comparison with other topologies, we can see that we can keep the core of the converter fixed. That is the coupled inductor. We don't need to increase the number of cores. If you recall from the few slides ago, when you are using isolated topologies, when you introduce an additional input, you would need to introduce another core or two for the primary and secondary side. So we were able to keep the passive components fixed. Possibly in the future, when the technology of designing flyback converters improves, this would be a very, very good and interesting topology to explore again. And then we can have high voltage gain by adjusting the ratio of the primary and secondary turns, and it's also buck boost because it's built on the principle of flyback topology, and you can boost the inputs using the multiple switches here. And the control structure is also quite simple, which we discussed in the paper as well. So I would like you to take a look. Another topology, which is not so much of another topology, but this is very, very similar. So what we did was to integrate a multiport converter with a multi-level inverter, which is one of the like a next step in integrating renewable energy sources, because first in the traditional systems we have conversion from DC to DC first, and then another converter which will have its own independent controller and everything to convert from DC to AC. So what we did was to integrate both systems, because in the many of the design or research of multi-level inverters, what was previously used was just assuming that the input sources was a simple or linear DC source, which is most likely not the case with renewable energy sources. So you are able to achieve some level of flexibility with the renewable energy sources here using a multiport converter, such as maybe MPPT control or some other kind of control system. And then you are able to regulate the voltage here. But one of the challenges with using multi-level inverters such as this topology is balancing the capacitor voltages. So in this topology, or in this paper, we explored the use of two different methods, either introducing an auxiliary capacitor balancing circuit as displayed here, or using a control-based balancing method. And in this paper, we saw that both methods were equally able to balance the capacitor. So the control-based method was by modifying the control of the multi-level inverter section such that the capacitor 2 was always balanced with C1 and C3, because if left on or uncontrolled, C2 will always discharge to 0, and then C1 and C3 will always share the voltage of the DC link equally. So, and this will impact on the waveform and the power quality of the AC power outputs on this side. So we use the auxiliary capacitor balancing, which introduces another additional set of switches and components, and compared it with using modification of the carrier waveform, or which is used to control the multi-level inverter. We discovered that although this gives better power quality responses, but the difference was very, very little. So we could just go straight to using the the, the control-based method, or also we were probably going to look into further analyzing this to see if there is actually more benefits to using the circuit as compared to the control method. But the circuit was very simple to implement as well. So it depends on the interest of the interest of the application in terms of, do you want simplicity of control or more complexity? Because of course modifying the carrier waveform is more complex in terms of control, and this just using the circuit is much simpler and probably more reliable, but that's a subject for future research. So one of the main advantages is low component count, as I've mentioned before, simple control structure, and then easy integration. So there is still access to the DC link here, and there is an AC link output, and then simple capacitor voltage balancing with no cross regulation. And after looking at unipolar DC source, DC link converters, we started to see some work on bipolar DC buses. So for those not familiar with bipolar DC buses, what you have is you have a positive pole, a midpoint, and a negative pole, in opposition to the traditional unipolar DC links where you just have a positive and a negative pole. So this is becoming one of the interesting areas that is being described as the future of DC power supply, power generation and distribution, in the sense that you have more reliability in this configuration, because when one pole fails, you can continue to deliver power with the other pole using the midpoint as the zero reference. And then in some applications, it's actually a requirement to have negative poles, such as telecommunication systems and aircraft power systems. They usually have a requirement, probably because of reliability. So even though when one pole fails, you can only deliver 50% of the power, but at least there is power that can be delivered, and you can reconfigure to still service the load as required. So because of this, we started to look at looking at multiport converters to see how we can have a multiport converter that delivers bipolar outputs traditionally without requiring another converter to convert the unipolar DC output. So one of the key features of this bipolar DC system, which I will also discuss in the next slide, is the easy conversion to AC, and then the increased reliability and efficiency, which I have mentioned before. So we looked at the possibility of using PV renewable energy sources such as PVs, fuel cell stacks, and wind. So for example, in this case, in one of the papers that we have proposed, which I will present just in a few slides from now, we integrated the multiport converter using a bipolar DC bus with a three-phase multi-level inverter, which with using the bipolar outputs of the DC bus, we were able to convert from the DC to AC. So it's integrated seamlessly with the three-phase multi-level inverter. So this is like one of the huge advantages of using the bipolar DC bus. So already the DC bus voltage is already in 3 levels, such that you have positive, you have a full DC link, and then you have half of the DC link in the positive side and half of the DC link in the negative side as well. So in to address this, we proposed in one of our papers, we proposed a family of non-isolated bipolar converters, multiport, and having balanced, symmetrically balanced outputs, such that by having symmetrically balanced outputs, we have both, as described here, the voltage on the positive pole and the negative pole must always be equal, and which is equal to half of the full DC link. And then there is, because this voltage must always be equal, there is the question of how to make sure that they are always equal, because in the literature, some converters have been proposed where you would need another complex controller to keep this voltage balanced. And if this voltage is not balanced, it will impact on the quality of power being delivered if the power is converted to AC, like I mentioned in the previous slide, where you have an integration of a bipolar DC system with a multi-level inverter. And also, it can cause overvoltage problems if some bipolar loads are connected to it. So there is the need to constantly keep this DC link balanced and symmetrical. And so there are several methods that have been proposed in literature. In this case, we use the Greenecher voltage quadrupler to keep this voltage naturally balanced. But as you can see, this requires the use of so many diodes and some capacitors, and so it further complicates and increases losses and reduces efficiency. And so in the same paper, we also looked at the possibility of using a synchronous buck converter, which uses far less components than these other three topologies, but it uses two controllable switches. So there is the introduction of a further complexity in terms of control versus no control complexity at all, because these are diodes and you just sort of leave them to do what they do. But one added advantage with using the synchronous buck converter is that the controller is very simple. You can use a simple proportional controller to keep the voltage balanced across the DC link capacitor. So when one of the capacitors is going out of balance, the current flows through the inductor and to ground, and then in vice versa in the other case as well. So this is a very interesting topologies that we have proposed in the Transaction of Power Electronics, also published this year. I would invite you to have a look. All these 5 topologies have different advantages. So for example, in terms of the voltage gain, this has the least voltage gain, while this has a higher voltage gain than this, and this last topology has even much higher voltage gain than all of the topologies. But also with the increasing voltage gain comes with losses. So depending on the application and what the application engineer needs, you can choose any of the members of the family that we proposed. And then more recently, we presented this topology in which is we started to look at the other side, because if you look at all what we have been doing before, we were looking at more non-isolated topologies, and so we looked at the isolated topologies using for achieving bipolar outputs as well, but using dual active bridge based topology with a multiple input ports. So we use it's basically an integration of like inverting DC buck boost DC to DC converter with multiple ports, with dual active bridge topology here, or you can also use a full bridge based topology by just changing the output cell, the output bridges. Instead of using active switches, we use diodes, and we're able to have a very similar performance in terms of output voltage balancing. In this case, the output voltages are naturally balanced because the midpoint of the converter, the ground point, is center tapped from the core of the transformer. So this gives a huge advantage because you do not need to worry about balancing the output of the DC bus. All you just need to worry about is the controlling the output voltage. And so with this topology, we can the plan is to further explore MPPT applications in the aspect of the inverting buck boost converter, and then leaving the controller of the active bridge, either full bridge or dual active bridge, to control the keep the voltage at the output constant. So one of the key features is that we have reduced number of switches in terms of the number of input ports. And if you compare with some of the previously discussed topologies of with isolation, you will see that we do not need additional number of cores or input or primary or secondary cores when we introduce another input to the converter structure, which will have complicated the whole control method and just make the whole system completely bulky. So we are able to keep a very simple converter structure and achieve high voltage gain by also either tinkering with the ratio of primary and secondary turns, or the voltage gain can be increased using by controlling these these switches as well. So for the relationship between the input and output voltages, I would recommend just having a look at our paper we just presented at the recently completed ICON in Belgium. And so for validating our proposed topologies, we have two main approaches. First is to, as a first stage test, is to test our controller using the hardware in the loop validation test setup. So we have this hardware in the loop system provided by Opal RT in our lab, the OP5700, and so we using a rapid control prototyping hardware controller provided by Imperix, we're able to send real control signals directly to the converter, which is implemented in the FPGA of the hardware in the loop device here, and this is our host PC for monitoring, and then we are able to monitor the waveforms for using the oscilloscope. We also have a more robust application, a more robust validation method, which we use in our lab, which is shown here. We have a low frequency switch bank. So these are real IGBT switches provided from Semicron, and we have the DC sources and load, and DC loads, DC sources as well, and we have some DC electronic DC loads. We have some resistive loads, and then we have the high frequency switch bank. This high frequency switch bank we're able to go up to 200 kilohertz using these switches made with the silicon carbide technology, also provided by Imperix. And then the controller that we use for the rapid control prototyping with the hardware in the loop device, we are able to also seamlessly integrate them with our high frequency switch bank because it has the optical fiber outputs as well. So we do both the hardware in the loop simulation, and we go one step further to validate the proposed topologies experimentally. And so bringing me to what I would say are challenges or opportunities, because in every challenge there is an opportunity. One of the key challenges that I would say we have discovered is that there are not many market available switches that we can use for some of our proposed topologies. And if we're going to be rethinking multi-port converters as a good way of integrating renewable energy sources, we need to also there is need to also go deeper into proposing or having more market ready, more options on the market in terms of the devices that we use. For example, when we look at reverse blocking switches, so far on the market, there's just this switch from IXYS, and it's actually not even really on the market because it's hard to get. So to implement this, we have to use a combination of a diode and another switch. So it's counterproductive in terms of multi-port converters, but this is what is available. And even in that case, the switching frequency is limited to below 20 kilohertz. That is if we were to use this product. So there is opportunity in proposing more efficient and much more attractive reverse blocking switches such as this, which would have maybe higher frequency switching frequency, maybe if made from silicon carbide. I know that there is some research that has gone into this in just research, but these are not ready, these are not market ready products yet. Also, in terms of the bidirectional switches, which I will say is more or less the ideal power electronic switch, there is also not much options available on the market. We have these products from Semicron. We actually have this switch in our lab, and but also its limitation is that it cannot go beyond 20 kilohertz switching frequency because it's basically a combination of two IGBTs or two IGBTs with two diodes as well. So in this configuration, this is the simple configuration, and you can see that in the same pack they're able to pack two different products. I mean, so almost like making it a discretized product. So there is an opportunity in moving one step further to having discrete devices that could even be looking like this, but having bidirectional possibility of operation in all four quadrants of the switching. So the only highlight key feature would be that it will have two gates for each either direction or either uh, operation of the switch. Another opportunity in multi-port converters is the proposed in the aspects of controller or controlling the converters, because already there is a lot of topologies that has been proposed. So I cannot really say that we really need more topologies, but rather we probably need more advanced or more simplified controllers which can take into account things like fault tolerance or distributed MPPT applications. So these are the main opportunities for improvement in multi-port converter topologies, as I can say. So distributed MPPT, because if you use a multi-port converter for maybe a cluster of PV systems, so you need to make sure that you're able to still derive the maximum power out of that PV farm or PV cluster. So we need to look more into designing controllers that are robust enough to include maximum power point tracking in them. And so, just in conclusion, I have included as a reading list the papers that we have, that I mentioned that we have proposed. Not all the references that are included here, but all the references that we have proposed are included in this reading list. You can have a look if you want the slides I can share with you. And so, thank you very much. I hope I didn't take too much time and talk too much, but I don't know if there's any questions. I would like to appreciate our sponsors for research, the Research Council of Norway, and our faculty and university as well. Here's my email address if anyone wants to just discuss further or collaborate. I guess that I am sure that we're open to collaboration, especially in terms of hardware in the loop application of these converter topologies.
Yeah, thank you very much for a very nice presentation. Yeah, I think a lot of the interesting topology related to the multiport DC-DC multiport converter. Yeah, so now it's time for the question. So yeah, anyone have a question, please raise your hand or turn on the camera and the micro and then make the question. Yeah, so during the everyone's prepare for the questions, so I have a question. So you can you come back to the slide 20?
Okay, just let me try. Okay, slide 20. Yes, yeah.
Yeah, so in here you mentioned the challenge and opportunity for the multiport converter, and I just have a question. So in the proposed multiport converter, so normally do you use the PI controller or what is the main controller you use for the proposed topology?
Yes, so for now we use standard double loop PI control. In some applications, you need a different kind of PI controller, or like the multi-input, multi-output PI control structure in some of the applications. But like I mentioned, that we were able to achieve simplified control, so we were able to keep the structure of the PI controllers, the standard double loop, single input, single output, but we're able to also still balance the power between the delivered by the input sources by just varying the ratio of the duty cycle. So I would invite you to just have a look at maybe the first paper, the one we proposed in TIE. It's very interesting how we were able to keep it as a simple standard PI controller. So, like I said, you can try to look at maybe model predictive control or artificial neural network controller or some other. So these are opportunities that still are very green in multiport converter topologies.
Yeah, thank you very much.
Yeah.
Yeah, I think yes. Yeah, I will take a look the details of the paper, but I think it's very good if we can use the PI control.
Yeah.
And yeah, I think there's still many the opportunity in the future.
Yeah.
Yeah, thank you very much. So we have one question from the audience. So yeah, Mr. Hua Dang Huang. So can you please turn on the video and micro?
Yes, I tried to turn it on, but for any reason I cannot find a way to do that. Actually, let me see.
All right.
So, sorry. Yeah, it's quite time.
Yeah, no problem. So yeah, please make the question.
Oh yeah, I see that stuff. Thank you. Yeah. Okay. Yeah. Thank. Yeah. So Emmanuel, yeah, if I'm
Yes.
pronounced correct your name, yes. It's Khoa. I'm from University of Huddersfield, United Kingdom. So, thank you very much for your presentation. That they show a lot of topologies, and some of that I think is kind of very interesting. I just want to check with you that because I think that you propose a lot of topologies, a lot of application. So, do you have a chance to kind of test all of your topologies to compare in terms of the efficiency of that?
Yes, this is a very interesting question because when you try to compare efficiency in power electronics with across topologies, you need to be careful because you need to be careful to use the same components exactly. So I cannot say, okay, my topology has higher efficiency than your topology, but maybe I use superior components like wide bandgap switches, which of course will have higher efficiency than somebody who uses traditional switches. So generally, I am always very careful not to use just efficiency as a blanket comparison factor across different topologies. But if within the same design and topology, like within our own paper, like in the family of converters that we propose, yes, we compare the topologies because, of course, we consider the same type of switches, the same type of passive components, capacitors and inductors. So yes, we compared. But of course, sometimes in publications, reviewers would say include the efficiency factor, but it's a little bit, I don't know, it doesn't make sense to me, like comparing just using efficiency as a blanket. But if you use specifically the same components, the same condition, and also the control can impact on the efficiency as well. So there's several factors that can affect efficiency. So it's across different papers. I don't like to always look at the efficiency value as at face value.
Okay, yeah. Thank you very much for your answer. Okay, I just have another question. Sorry, yeah, it may take a long time than the other. In terms of the controlling, some topology look quite interesting, but because a lot of components there mean that more complicated in terms of controlling. So, do you have any comment on that? Compared with that some kind of that dual active to rich and that at the moment conventional. So in terms of controlling, do you think is that doable or not?
Yes, in terms of controlling, I would say that all of the topologies that we have proposed, the control is doable. Some might be more complex than the others. And the interesting thing is that the more complex the control topologies that seem to require more complex control actually provide more advantages. So if I can show you in this slide, like I mentioned, looking at this, you can use the phase shifted control of the dual active bridge to, regulate the output voltage, right? So you can also regulate the voltage of, let's say, VG, right? By controlling these switches. So by so doing, you can implement MPPT control here for the input sources, for example, while being able to regulate the output voltage. So you can now combine voltage balancing, like keeping voltage constant with MPPT control. So although the controller looks complex, and it's basically just two different simple controllers, right? So it gives you the added advantage of being able to combine MPPT control and output voltage balancing. I don't know if that clarifies or answers your question.
Yes, yeah, it is. Yeah, okay. Thank you very much for your answer. Yeah, wish you all the best for your future.
Thank you.
Thank you.
Yeah, thank you very much for the question and answer. And yeah, anyone, do you have any questions? So yeah, we have time for that. Yeah, I just we are waiting. So I just have the small question. So you mentioned like for example, we use the MPPT to control in the, how to say, the input side to select the maximum power. So in here, for example, we combine the battery and, for example, like the battery and also the supercapacitor, for example. So, and maybe some other. So is there any problem for that, or is
Okay, so for example, you know that in terms of battery, we don't need to look at maximum power point, for example, right? We just need to generate the required energy, and maybe when you combine battery and supercapacitor, we can do peak power shaving. So the supercapacitor supplied a much higher power and much higher frequency, just like Mr. Bank presented, right? So we can do that between battery and supercapacitor. And then when you integrate something like solar in that kind of system, the focus of MPPT control can be on the solar system, the PV system side. So the MPPT control will be designed in such a way, or the control of the converter will be designed in such a way that the converter, the duty cycle of the switch controlling the input. So let's assume that V1 is PV, right? And V2 is battery, V3 is supercapacitor. S1, which controls V1, is always switching at a duty cycle that makes sure that maximum power is delivered from V1. It's as simple as that. So if we have a duty cycle that, if we have a general duty cycle, so if you look at the paper, it will be a little bit more explained. The duty cycle of S1 will always be varied in such a way that it delivers maximum power from V1, and then the others can be controlled to just balance whatever power is left unsupplied.
Yeah, I understand. Yeah, that's very interesting. Yeah, thank you very much for the answer. So yeah, is anyone have the question?
Bang here.
Okay.
Yeah. So
yeah, Mr. Bang Nguyen, please.
Yeah, can you hear me?
Yes, I can hear you.
So so here, like, just a small question first. So in the suite of S1, S2, and SN, in the figure here, you use a unidirectional suite, right?
Yes, yes.
Yeah.
Yes, so we can only use PV, wind, or fuel cell systems. We cannot introduce battery in this topology. But if you recall, in like this topology, we can, because we use bidirectional switch, we can use battery and supercapacitor or other energy storage systems. I guess that is your question, right?
Yeah. So in this case, we have to, like, careful to prevent the short circuit between two. So yeah.
Yes, yes. But the interesting thing is that there will actually not be short circuit because it's a reverse blocking switch. It's not the
Yeah.
traditional IGBT with anti-parallel diode. So there is some kind of small diode here that makes sure that there is no reverse current.
I see.
Yes. So when this switch is off, it's totally off because there is a diode blocking the flow of current back into this system. So it's more or less like they cannot be short circuit. And then in the commutation of these switches, you can the only thing is that you have to make sure that the source with the highest potential turns off first, so that the other sources with lower potential can supply right after. That's in simultaneous operation.
I see. Yeah, thank you.
Yes, yes, yes.
Okay.
Yeah, thank you very much for question and answer. And the time is of the webinar is close to the schedule. So if anyone have a question, we have maybe time for one more. We can, if no questions, so we can close the webinar. Yeah. So yeah, the chairman. Yeah, do you have any comment or something? Yeah, please.
No, it's fine for me. I only concern his football skill every year, not about the research level.
Yes,
Yeah,
and unfortunately, in the past 4 months, I have been in Canada where they seem to like, I don't know what's the name of the sport more than football. So.
Yes, that is our main concern in the group activity. How well he performing the football.
Yeah, so I think the main content for webinar, yeah, already complete. So I just have the question for the not the research. So I see the how to say the information. So it look quite so busy, like you work like the research and also like the work part time in the worldwide. So is that very busy for you or no problem?
It's not. I cannot say it's too busy, but there's a good. The work with the bank sometimes is very like industry focused, so it helps to build a bigger perspective in terms of how the application of all these things we're doing in the research and what do the people really care about. In the end, the people just want to pay less for electricity. So they don't care about efficiency or anything or cross regulation. No, they just want to know how much will I pay per kilowatt hour. So that's like, so it's not too busy with the World Bank. It's just part time and maybe some few days in a month. So it's an interesting experience anyway.
He are not allowed to say he's too busy.
Yeah, anyway, yeah, I think very interesting and very good experience for the future.
Yes.
Okay, thank you.
Thank you.
Yeah, thank you very much for attending the webinar today. Yeah, so we are going to close the webinar at the schedule. And yeah, so we have still remain some people. So if you have time, we can take more, how to say that, 5 or 10 minutes or like just a free talking for connection. So I think I first time talk with Mr. Hoa Đăng Hoang. And yeah, Frank, yeah, we didn't talk. So if you have some information or can you talk something? Yeah, so now you work in the United Kingdom, is that correct?
Oh, okay. All right. Yeah, sorry for that. Yeah. Oh, at the moment I'm work in the United Kingdom. Yes, I graduated from University of Sheffield in 2011, and after that I go from around 11 years in university, but with industry projects. So I lead in terms of the technical side of I think I cannot remember exactly, but I think around 4 multi-million power projects. Focusing on of that is in terms of the electrification of electric vehicle. So let's say the powertrain, the traction machine with low cost using ferrite, or then controlling of the full electric vehicle. Then the other moment I joined University of Huddersfield and also work with the same area, but go a little bit further in terms of the smart grid, microgrid, and battery, secondary, and the other moment, the most interesting area I'm working is the fuel cell. Yeah, because I think on my opinions, fuel cell is the future.
Yeah, thank you very much. So I think you move to a very, how to say, hot chain now. Yeah.
I hope so. Yeah.
Yeah.
Yeah, nice to know you, Khoa.
Yeah, very nice to meet you. Yeah. Yeah.
So are you looking in the fuel cell? Are you looking with like hybrid fuel cell with like supercapacitors, or just fuel cell directly? Because I know the power density of some fuel cells are quite lower than.
Yes, in terms of the fuel cell, if you want to install that in the powertrain, you also need to come together with some kind of energy storage, because fuel cell cannot take your energy back when you try to regeneration.
Yeah.
And that regeneration is very important on any kind of transportation application.
Yeah.
So you only need to mix that to, let's say, the battery or supercapacitor. Yeah. And then you need to balance the energy flow on that.
So I just have a question, like a technical question. So between the fuel cell and the battery, do we need the isolation or not?
Yes, you need some kind of not isolation, but you need to do the balance in terms of the level, because the voltage level of fuel cell and then the voltage level of the battery or supercapacitor, they always not the same. So you need to do some kind of controlling to make sure that the DC link level, the one you supply to the inverter for the traction machine, must be balanced. Yeah.
Yeah. Thank you very much for the sharing.
Yeah. You're welcome.
Yeah. Yeah. So is anyone has some comment or something to talk? Yeah, because we very in the very close research. So yeah, I think very quite interesting.
Yes, we may activate some core work if we find some common topics. I think that would be the best.
Yeah, in terms of the research or any kind of collaboration, for example, I just got the fund from UK with Ho Chi Minh City technology, I think Bách Khoa, in terms of the microgrid for a year. So it means that a lot of collaboration in UK and Vietnam. Sorry to say that, because we Vietnamese Mr. I think Amonu. Yeah. So if any kind of collaboration we can think about, just drop me an email. Thank you.
Yeah, on smart grid and on which direction you are looking
the one we just successful and got the confirmation that that's the kind of microgrid, because we think about using the biogas from the farm in Vietnam to generate for the for the generator using the biogas, and then combine that with solar PV power using the battery as a secondary life. So the one used from the electric vehicle after 5 to 7 years. So you can try to, do the step health, and select which ones still can be reused. So we can use that for energy storage. The cost of that around just 30% compared with the new one, the full, brand new. So that's the kind of the cost-effective microgrid. I think we can propose on that.
Okay, quite interesting. Yes.
Yeah, I hope so. Yeah.
Thank you very much. So time for family now. Have a nice weekend. Bye bye.
Yeah, nice weekend to you. Yeah, thank you very much. Yeah.
Thank you. Bye.